Hello guys, hope all of you are doing great. In this part of the video, we'll be seeing or we'll be learning how we can train a very simple neural network that consists of only one neuron for this single training example. You see here, this neuron, let's first see what does this neuron do. This neuron, this neuron takes two input, A0 and A1. I'm writing I'm labeling the inputs as A0 and A1. You can think it of like activation 0 and activation 1 from the previous layer. And then these inputs are connected with the neuron through some weights, say W0 and W1. And also the neuron is connected with a bias, say for example, B0. And then what this neuron does is it takes a weighted sum of the inputs and the biases. You see here, what does this neuron do first? It computes A0 into W0, that is this input multiplied by this weight, then plus A1 into W1, that is this input multiplied by this weight, and then plus B0 into 1. This B0 into 1 means ultimately B0, but why am I writing? You can think it of like, okay, this B0 is actually a weight that is connected with a neuron whose value is always 1. Okay, so we write simply B0 there. And this specific, input is known as the bias of the neuron. Each and every neuron in a deep learning network, they will have their own biases. Okay. So point is that what this neuron is doing at first is that it is computing an intermediate result. You can think it of that way, which we are labeling here as Z is equal to, which is what is that intermediate result? That is the weighted sum of its input. Why am I saying weighted sum? Because it is weighted sum. You see here, what you can interpret this thing is as like G is equal to some part of the this much of weight 0 part, or weight much W0 much of this A0, and then some fraction of this A1 and this whole of this B0. These are the weights, so that is why the Z is a weighted sum of its input. Now once that weighted sum of the input is computed, what this neuron does is it passes that weighted sum through an activation function, or through a specific function, and the name of that specific, or we refer to that function as the activation function of the neuron. Now see here that you can use, or one can use different activation function, and for most of the neurons, actually, this activation function is a nonlinear function. Nonlinear function in the sense that the output of these activation function, they do not depend on Z linearly. Okay. So the importance of this nonlinear function at this point of the neuron, I mean, why we need these nonlinear functions, that will be the story for some other video. But for the time being, I just request you people, you just like stay with me when I say that this nonlinear activation function is very important here. Without this nonlinear activation function here, artificial neural network would have not been possible. Okay, so for most of the cases. Now, okay, now what this neuron is doing is that it is taking a weighted sum, then it is passing that weighted sum through a nonlinear function, which we call as the activation function, and whatever it is the output of that nonlinear function, that neuron generates that output as its output. I mean, that will be the output of the neuron. Now see here, here we are talking about a neural network that consists of only one neuron. So these inputs to the neuron is basically the same, the inputs to the network itself, and the output of this neuron itself is the output of the network here. Okay, but here I'm writing this O. In this specific example, this O is same as the output of this this specific neuron. Let's call it the output of this neuron is actually activation 2, say A2. I'm giving it a name, but A2 and O is same in this case. But suppose you assume that you have a neural network where you have many neurons and many layers are there, then this O will be considered as the output at the final layer, the last layer. Okay, so whatever it is, that is considered as the output of the neural network. Okay, now that's done. Now, what we want is neuron. See here in our neural network, we have only one neuron. So we don't expect the neuron to learn any general thing, but we just want this neuron to learn this specific example, specific training example, where A0, that is this input, is equal to 0.25. Sorry. When this input is 0.25 and this input is 0.15, we want this this network to generate this output as 0.037. Okay, that's what we want this neuron or this network to train for. Okay, now we know what we want, and we also know like what is this what is the internal operation, or what internal operation this neuron is it's performing on its inputs. Now the next question is that how we are going to do this. Okay, like what should be our strategy to achieve that thing. Okay, that is when I say like we want to train this network, for this input and output. It means that like whenever we give this network this input, it will produce that output. But the thing is that we'll not tell the network what is this W0, W1 and B0. And the goal of training for this network is to figure out what is this what are these W0, W1 and B0. Okay, and that's what we want to achieve. That is, somehow we want this neuron to figure out what is this W1 should be, W0 should be, and B0 should be. We are not going to tell it these things. We'll only tell it what is A0, A1 and Y. Okay. Okay, then how we are going to do it? Is there a systematic way of doing that thing? And yes, it is there, but for that we need to bring here another concept. You know that, and that concept is the concept of the cost function. Okay, now let's see here how cost function, how bringing a cost function here helps us helps us take a systematic way, by following which we can actually update these weights W0, W1 and B0 systematically, so that at some point of time we reach at a point where the combination of all these three with this input more or less gives you this particular output there. Okay, let's see what I mean by this actually. And okay, now let me bring here the the cost function. Now what this cost function is doing is that, okay, see here, suppose what we want the neuron to learn is, or network to learn is that, okay, what are these specific values of B0, W0 and W1. But at the beginning, certainly this network doesn't know anything, and since we are not saying or we are giving any information, the network will assume, okay, they have their own random numbers there. Okay, W1 is a random number, W0 is a random number, B0 is another random number. So using that, obviously now using those random numbers with these A0 and A1, the network will be, now see, those are things it needs for its computation, so it can do this computation and it can generate an output. The thing is that once that output is generated, like say you can consider, like say for example, what I mean is W0 is equal to maybe 2, or W1 is equal to say 3, and B0 is equal to, for simplicity, say 0. Then in that case, what it will do is like 2 times this 0.25, which is 0.5, plus 3 times this 0.15, that is 0.75, and sorry, 0.45, say. Okay, and then plus 0, and that is equal to 0.95. So that is the output which is generated with this W0 and W1 and B0. But 0.95 is not our desired output, right? So it's a wrong output. But only saying it is wrong or right, this cost function allows us to say like how wrong it is, how much it is wrong, like now how far it is from the actual output. That's what we want this cost function to tell us. So basically we want these cost functions so that it can give us a quantitative measure of the error of that particular of the network, okay, for that specific input. Now here, see, one thing I want to tell you, this cost function in general, I'm talking about till now this cost function as a general function. So you can consider any function as a cost function. I don't mean like any function, means at least you can have like potential candidate functions there which you can use as a cost function. But most commonly used ones here I'll be using directly. And first, you see here what we want our network to produce. We want our network to produce a real number, y equal to 0.037. That's what we want to produce we want our network to produce. So if it is the case, like if you want your network to produce some continuous real number, like everything is fine, like if it generates the output as 0.0374, that's also, if you want the network to produce as an output, or maybe 3, maybe 0.037544444321, like that, like all these different values are possible. In that case, that is, if the output of the network is a real number, in that case what you can do is that you can use a cost function. Now, very commonly used one is this mean squared error cost function. In mean squared error cost function, what we do is whatever it is the output generated by the network, from there we subtract whatever it is that we want the network to generate, and then you take the square root, or you take the square of that difference. Okay, and that square of that difference is called as the cost of the network. Okay. So for example, here, suppose assumed the W0 is this, W1 is this, B0 is this, the output is 0.95. So in that specific example, cost will be our 0.95 minus that y, the actual y, 0.0375, and then whole square. So whatever it is, you have to compute it. But one thing we know, that that's a positive number because we're taking the square, so certainly it will be a positive number. Okay. Now you see, instead of looking at this specific cost, let's like try to plot this cost versus this output. You know, this cost is now, it's a function of the output generated by the network. Okay, so in that case, if you plot the cost versus the output, say for example, this is output and this is the corresponding cost, say. So in that case, one thing you realize or see here, or you can observe here, is that whenever the output of the network, whenever this O is equal to 0.0375, that is, say for example, this point, whenever the output is equal to this particular point, the cost is 0. Obviously it is equal, the cost is 0. Not only that, if you see, if your output, generated output, deviates from this desired output in both the direction, like positive and negative, you see you'll be seeing a positive cost because of this square you're taking. And that function will certainly, you can make it like, obviously you know that the function will look something like this. If you plot for different O values within a range, then you will see, okay, that is the cost function looks like. Okay. Now you see here, from here, now in terms of the cost function, you can represent your network. Okay, so now instead of saying that we want our network to produce this output with respect to this two input, we can say that whenever we give this input, we want our network to adjust this or learn these weights and this bias, so that at the end, if I compute the cost, that cost should be minimum. And we know, like, the cost minimum value of this function is 0. See here, it is same as actually saying that we want our network to produce 0.0375 as the output. But now this time we are sort of defining the goal of the network in terms of the cost function. That is, we have this function setting their cost function. The network can assume anything as W0, W1, and B1. We give the input with those with those 0, 1, and 2, W0, W1, and W, all the weights and biases. Basically it computes the output, and then we can give that output to the cost function, and the cost function gives us a number that says, okay, the output is good, output is bad, we still can achieve more in terms of the cost. We still can reduce the cost. Actually, we still can reduce the error of the network. Okay, so now we are defining the network in terms of this cost function. Now, as I said, now I'm repeating it one more time, that now this time what we want is that, okay, it has to learn these weights and biases such that at the end, if we compute the cost, we want the minimum value, the value of the cost should be minimum. That's what our goal is, right? Now, as soon as we define the goal of the network with respect to this cost function, it gives us a way of adjusting these weights and biases, in a systematic way, so that we can achieve that minimum cost goal. It is basically, now it's a function of optimization. We want to now set these values W0, W1, and B0 so that the value the value of the cost function is optimized. In this case, we are looking for the minimum value, so it becomes 0. Got it? And that's why, defining the problem in that way helps us, because there we have a standard way of doing it. That standard way is gradient descent. Okay, so let's see what gradient descent says you. What gradient descent tells us is, like, if one is interested in finding the minimum of a function, so the way we want to achieve here, the minimum of the cost function, we want to minimum of this cost function, we want to like minimum of this cost function we want to achieve. In that case, what we can do is the steps should be in the opposite direction of the gradient of the function with respect to a specific parameter. Here it might not be an accurate definition of the thing, but the point here, what I want is, when I say the steps, it means gradient descent allows us to reach the minimum or the optimum of a function by taking small steps. And what it says is that, like, okay, if that this function, if that cost function, like c, is a function of some parameters, say for example, in this case, see here, cost is, although it seems like it's a function of o, since o in turn is a function of w0, w1, and b0, or we can say like cost is a function of all these three parameters, and they all generate this the ultimate value there, okay, ultimate output there. Now what it says is that if we want to minimize the cost function, then in each step, if we take like steps in the opposite direction, of the gradient of the function with respect to a specific parameter. That is, if we like compute the gradient of this cost function with respect to w0, with respect to w1, and with respect to b0, then we get actually the gradient of the function with respect to all these three different parameters. Now, using gradient descent, what we can do is, those gradients we can subtract from the previous values to to move one step closer to the optimal solution. But the point, what am I saying you is, okay, now if it is not clear, you see here what basically it is saying you is that it says you that, okay, now you see one thing is clear in your mind, that cost is a function of w0, w1, and b0, right? So cost is a function of w0, w1, and the b0 of the network, and we want to find the minimum of this cost function, with respect to o, but o is again depends on all these three terms. So what gradient descent says is that if we want to achieve that thing, then what we have to do is we can do something like this. From this is you just can start with any random weights there like this, and then in each step, or you can say like in each iteration, or you can do it like repeatedly, one iteration, then you repeat the same process, another iteration, and another iteration. So you become closer and closer to the minimum of the function. So so what we can do is, whatever it is the previous value of that particular parameter, from there we subtract a constant, we weight a constant. For the time being, let's consider it as a constant multiplied by the, see here, in the opposite direction of the gradient of the function with respect to that specific parameter. So multiplied it by the gradient of the function with respect to specific parameter means basically it is saying that rate of change of the cost function with respect to w0. If you want to change w0, then what we need to do is, first we have to compute the slope of the function with respect to that parameter. Then we will take a constant, we'll multiply a constant with that, and then we'll subtract it from the previous value. Now why we are subtracting here? Because we want to move the opposite direction of the gradient. That's what I mean by opposite direction, in the sense that you see here, if this term is a positive number, then we are reducing w0, and if it is a negative number, then we are increasing w0, because that minus will be multiplied by this minus, it will become plus, so we are actually increasing w0. And this eta is a constant number, as you in my previous video also I said you that eta is represented by eta is said to be the learning rate of the network, and this eta is constant for all for the entire network. There is only one eta. Okay, so this is known as the learning rate, or you can think it of like the step size you take in each iteration. Okay, now the second point is, if you now want to update now this w1, what you have to do is w1 minus eta into rate of change of that cost function with respect to w1, and b0 is b0, whatever it is previous value, eta into rate of change of the cost function with respect to b1. So these three terms we are writing, and now we can write it in this way because of the gradient descent algorithm. That says us like, okay, if we do something like this and if we repeat this process, quite a good number of time, then what we can expect is that our cost will at some point of time reach this minimum value. We can expect that. Okay. So now we know, like, okay, like let's try to summarize the thing. What we want our neural network to do is that, okay, we'll give this input. It has to adjust these weights and biases in such a way that at the end, if we compute the cost, we'll get the minimum of the cost, the zero. Okay. And since we have to like optimize now this cost function with respect to these weights, then obviously we can use this gradient descent algorithm that allows us to update the weights in a systematic way so that we can expect to reach the minimum of the function. Done. Now, more or less, now we know like what we want to achieve and what is the systematic way of achieving the thing. But still, there is one question left. Now, how we compute this, the rate of change of the cost function with respect to all these different parameters. Now, see here, right now in our network, only we have only three parameters: W0, W1, and B0. But suppose you consider a big network. In that case, certainly you have like millions of all those different parameters there. So there also you have to actually do these operations. Like for all of them, you have to compute the rate of change of the cost function with respect to those parameters, and then you have to update those parameters. And that's what it is. It is done in the backpropagation or in the backward pass of in a training phase. There, like in a training phase, there's this forward pass where we compute the output. Then there's this backward pass where we sort of propagate back the error through the network to update the weights and biases of the network. Okay, so that's what it is done here. And propagate back the error through the network is like these things. Now, from the weight, we basically subtract the rate of change of the cost function at that point with respect to any specific weights there in the network. Okay, and we do it like step by step. First, we do it in the last layer, then the second last layer, then the second to second last layer, like that. Okay, and that's why it's sort of like the backward pass there. Okay, don't worry. Like, if things are not clear, but then you just try to focus only on this specific example. And once you understand what is happening here in this specific example, then certainly you can expect like the same understanding you can more or less generalize to understand what is happening inside this deep neural network. Because you see here in a deep neural network, you will see the same neuron, like same type of neuron that takes a weighted sum. All these neurons are basically doing the same thing. It takes the weighted sum of its input. It passes that weighted sum through an activation function, usually non-linear activation function, and it generates whatever it is the output of that activation function as the output of that neuron. And then that output becomes the input of some other neuron. Then the same thing goes on till the output layer. Okay, and at the end, at the output layer, we compute the cost, or we want to minimize the cost. So the same approach is taken actually. Okay, understood. Okay, now let's see. Once we know, like, okay, we want to compute this we want to compute this rate of change or the slope of the cost function with respect to all these different parameters. Let's see exactly how we can do that. Okay, now let's bring this network. Let's bring this network down there. Like, okay, now we want to compute the rate of change of the cost function, rate of change. Suppose now we want to compute the first one. Three things we have to compute, right? With respect to B0, I mean, how much we want to update W0, W0, W1, W1, and how much we want to update this B0, right? Now, let's start with this B0 first. Rate of change of the cost function with respect to B0. Right, like if I do a small change here in B0, how much the cost function changes. That's what we want to compute. Now see, as you can see here, this cost function is not directly a function of B0. So directly we cannot write here any specific equation or something there. But what we know here is that this cost function depends on this O, the output of the network, where the output of the network again depends on this intermediate result Z, and that intermediate result Z depends on this B0. You can see a like chain of cause and effect, cause and effect. That is, if you change something here, it will change z. If I now that change in z will again in turn come do some change in o, and obviously that change in o again in turn will do some change in the cost, right? So that chain of events you have to follow. So what we can do is that rate of change of the cost function with respect to b0 we can write in this way. That is, first we can compute what is the rate of change of the function, cost function, with respect to this o, and that is this o there, and then what is the rate of change of the cost function with respect to what is the rate of change of this output now with respect to the intermediate result g, and what is the rate of change of this z now with respect to b0 there. You see here, rate of change of this cost with respect to o with respect to z, and z with respect to b0. Okay, now see, this z directly depends on b0, so you can write this form, and o directly depends on z, so we can write it. So c directly depends on o, so we can write it, right? So let's try to write it. Now, what is the rate of change of the cost function with respect to the output? So this is this thing now, rate of change of the cost function. And again, just for one quick note, that this thing, expanding this derivative in this way, in this form, is known as the chain rule of differentiation. Here it says chain rule, like you're differentiating each link there individually. Okay, and if you even do not know anything about it, you just can see that this do gets cancelled, zz gets cancelled. The only thing that remains is dc by db0, which is this that we want, right? So that's a side note. I guess people know that. Now you see, now we are interested in these individual terms. Now rate of change of the cost function with respect to the output is, we can express it, right? Rate of change of this particular term there with respect to output. And you see here, y is a constant in this case, so it will become like 2 multiplied by o minus y. And again, if you have seen my previous video, and just even if you have not seen, you just can believe me that mathematics allows us to cancel this or ignore this too. Simply we can write this thing as o minus y. It allows us to ignore this constant. Why? Because you see, we could have easily written our cost function as not o minus y whole squared. We could have written it easily like half of this, and that half, if it is there, then this half will be here also, so 2 gets cancelled. So that way mathematically you can justify, okay, why we're cancelling that particular term. Okay, but I guess you're comfortable now, right? Yes. Okay, now rate of change of the cost function with respect to the output you have generated, like we know, like we can write it in terms of available things there. Now again, similarly, you can write now what is the rate of change of the cost function with respect to g. That is the question now. You see, what is the rate of change of the cost function? What is the rate of change of this o? How much this o changes if I do a small change in this z? And obviously that depends on what activation function we are using. If you're using you appreciate that point, right? Like the rate of change of this output with respect to z is nothing but it is the derivative of this activation function, right? So instead of writing it in a specific form, for the time being, I'll obviously write it in a specific form when at some point of time in this video. But for the time being, what you can consider is that, okay, let's give it a name. Say, let's call it this. It is the activation. It is the differentiation of the activation function, or derivative of the activation function that I'm writing is as activation dash of activation function. Say for example, input is z, and I'll come to that point. But here what you see is that this is basically the derivative of the activation function. Okay, so it says that, like, this is the derivative of the activation function, means how much the output of the activation function changes with respect to z. Okay, it means it is basically computing this d of activation of z, how much the activation value of the activation function changes with respect to a small change in g. That's what we want to compute. And as I said, now these activation functions, you have different candidates there. Like, say for example, you can use a ReLU or you can use a sigmoid function. So there these this term will change actually. If it is a ReLU, then the expression will be different, and if it is a sigmoid function, the activation will be the expression will be slightly different. Okay, but for the time being, what we can think of is like, okay, rate of change of the output with respect to G, we are writing it as activation dash or activation prime of Z. That basically says us like what is the rate of change of this function, the output of this function with respect to G. Okay. Now, having said so, suppose we have computed this, we know how to write it at least, and then the final question is this: what is this dg by db0? Okay. Now, what is this dg by db0? You can see now what is this dg by db0. You know that already, right? Like it is dg. Now, what is this z? This is like, you know, weighted sum of all these terms, like, you know, a0 into w0 plus a1 into w1 plus b0 and with respect to b0. Now you see that there is no b0, so they do not change. The rate of change is 0, only this b0 is there. So this function, rate of this function with respect to b0 is 1. Okay, ultimately it is like asking the question, how much is db0 with respect to db0? So it is 1, right? Okay, the rate of change of this g with respect to b0 is 1. It turned out to be, this is 1 now. Okay, we have computed this thing to be 1. We have computed this thing to be, for the time being, as the, you know, the derivative of the activation function, and this term to be o minus y. So if you multiply all of them, it looks something like this: o minus y multiplied by whatever it is the derivative of this activation function and multiplied by 1. So 1 you write, you don't write, basically the same thing. Okay, got it. Now we know what is the rate of change of the cost function with respect to b0. Now it's time to compute what is the rate of change. Now we have to do the same thing. Now we have to do it for w0 and w1 also. So let's try to do it, and it's simple now. If you have followed up to this point, if you have understood, things are simple now. There, it's dw0 by, we want to compute the rate of change of the cost function with respect to dw0, which is equal to, you know, the same chain rule. It's the same thing we have to do. See, we want to compute the rate of change of cost with respect to this w0. It means how much the C changes with respect to O, how much O changes with respect to this activation function, and how much that with respect to that activation function, and how much that activation function changes with respect to what I said. Yes, I'm sorry for this. How much this cost changes with respect to O, how much O changes with respect to this Z, and how much this Z changes with respect to W0. That's what we want to do, isn't it? Same thing. We just write it, the chain rule first. The rate of change of cost with respect to O, because O, C directly depends on O, so we can write it. Rate of change of O with respect to G, like how much the output changes with respect to Z, and then how much this Z changes with respect to W0. And see that G depends on W0, O depends on Z, C depends on O directly, so we can directly write their expression. And we already have computed dC by D0. You see dC by D0 here only, so we can write O minus Y, that we know that. And we also have written like what is dO by dZ. In that case, we are writing for the time being as activation, derivative of the activation function. And then what is now the question is dZ by dW0. Here, see, it is dZ by dW0. If you want to compute, if you want to compute, then it is see here now dZ by, instead of writing dB0, we're writing dW0, and you can see that A0 W0 plus A1 W1 plus B0 and dW0. You see, only this term has W0 and they do not have W0, so they are all 0. So rate of change of A0 W0 with respect to W0 is A0, the corresponding the input. See, we are how much we are to change this thing, that depends on like what is the value of A0. Okay, so that's interesting actually. So OY and activation, and then G with respect to W0 is the corresponding input through which it is connected. Okay, done. Now similarly, if you ask like what is the rate of change of this with respect to W1, you can directly write it. And the first part is same, rate of change of O with respect to C with respect to O multiplied by the rate of change of O with respect to G with respect to g, and then how much this cost function changes, or how much this z changes with respect to w1. So if z changes with respect to w0 as a0, I mean it is equal to a0, then obviously rate of change of this z with respect to w1 is a1, right? I mean, that's all then, a1. So we now know how to compute these three terms. Then we now know how to compute this term, and this term. So basically now we know how to compute all the things. It's now only the time. Only thing that is left now is that write some code and ask the computer to perform these operations. Okay, but before writing the program, let's first summarize like what exactly it is that we want our program to do. Okay, so what we want our program to do is, the first thing is that we'll have something called as eta, the learning rate. This is a hyperparameter, like let's fix it 0.01 or something. You can change it later on. And then you have something called as epoch. Why we need this epoch, I'll be like saying you in a moment. And then we have something called as, these are two hyperparameters, and also we need to have some random values for this w0, w1, and this b0 there. So we have some random values. Say, let me write it here, like say 1, this is 2, and this is, say, for example, 0. Biases are usually set to 0 at the beginning. Now what we want is, we want to do a forward pass. Okay, so in forward pass, what we want our neuron to do is, our network to do is, see here, only the neurons operation itself is the only one operation that we want our network to perform. So let's do it. In the forward pass, what we want is, we want to compute the output. Output will be equal to whatever it is, also we have these inputs. We have this input a0 equal to whatever that number, a1 equal to whatever that number, and also we have this output that we want, whatever that number. Okay, so O will be computing it in this way. W0 multiplied by A0 plus, okay, instead of writing that thing as O, what we want to do is that, okay, I'm sorry. Okay, let's do it. Sorry, I don't mind. The forward pass, in the forward pass, what we want to do is, okay, we have this A0, we have A1, and we have this Y also. These are inputs. I mean, we already have that. And the forward pass, what we want is, we want to first compute an intermediate result. So Z is equal to W0 multiplied by 1 plus W1 multiplied by, sorry, not 1, W0 multiplied by A0 plus W1 multiplied by A1 plus plus what is that, b0. Okay, this is our G intermediate result, and then we want to compute the output, which is nothing but the activation function. We pass this input now through this activation function. Now if we want to implement, then we have to be specific. I cannot simply say activation function. It's a function, it could be anything, or there are many potential functions which can act like an activation function. But here, if we want to implement it, you need to be specific. So let's be specific. Suppose for the time being, let's start with ReLU. Then we want to implement this activation function. Basically, here I'll be replacing it by, say, for example, ReLU and G, where ReLU will be a function that I'll be writing. So I'll be writing like, say, define, or here I'm not writing in terms of code. Let me write it in this way. What is this ReLU of Z is equal to, what is ReLU? It is like if the input is greater than or equal to 0, it is same as the output will be same as the input. Okay, so it means this value is same as Z as long as Z is greater than or equal to 0. Okay, and it is equal to 0 otherwise means when Z is less than 0. Okay, so if you want to plot the ReLU versus if you want to plot this Z versus ReLU, then you will see that, okay, for all these negative Z's, the output is 0, and as soon as it becomes positive, the output will be same as the input, so it will be aligned at 45 degrees. Okay, so that's ReLU. So we'll be defining a function here, ReLU of Z, that will perform this operation. It'll check if the incoming value is greater than or equal to 0. If it is the case, it will simply return the value, otherwise it will return 0. So that will be the implementation of ReLU. Clear? Okay, now we have computed the output. And in the same go, you can write here the sigmoid function also. That I'll not take care of when I'll be actually writing the code there. Okay. Now see, we have computed the output, and the next task is, for our sake, we can see how good or bad the output is just by computing the cost. So we'll be writing here, say, now we'll be computing the compute the cost of the network. And how do we do that? We'll take this O, this is cost, is equal to whatever it is, this O minus whatever it is, this Y that we have. We'll take this and we'll take the square of it. That's our cost. Okay. And that's okay, fine, say. And then the next step is very important. It is your backprop now. Backprop algorithm. Backprop algorithm means we will now, since we know the cost, it is time to propagate back the cost through the network, to the beginning of the network. Since there is only one neuron here, things are very simple. So what we have to do in backprop is basically our goal is that we want to update the weights and biases of the network. So for that reason, what we'll be doing is that, okay, first we will be computing these terms there. First, we'll be computing what is this rate of change of all of them. Okay, let me write them. Don't worry, it will not be very long. Let me write it. In backpropagation, we can compute like this. We have to compute this actually. First thing is that what is the rate of change of the function? Say, let's call it say, rate of change of the cost function with respect to B0 that we have seen is output minus Y. That's this up to this cost to output level, and then output, that thing we have to multiply by the now see, that's where the specific version of this derivative of the cost function is coming. You see here what we initially wrote it as, like rate of change of the cost function with respect to B0 as O minus Y multiplied by activation prime of Z. Now it's time to reveal what that activation prime of Z is. Activation prime of G. Now what is this activation prime of Z? So whatever it is, now it depends on what activation function we have used here. Okay, so let me write it here now, the specific version, O minus Y multiplied by now the derivative of that, I mean derivative and then G. Now let's see what exactly that thing is. What we want, what is this activation prime Z? I wrote as here somewhere. Here it is actually rate of change of the activation function given that input as Z with respect to Z itself, right? So it means here that suppose now if we want to implement it, we have to write the code for it. So we'll be writing what is this derivative of Z is equal to derivative, this is suppose a function derivative of G, it is equal to what? It is equal to, now what is the rate of change of the ReLU function? You see here how much this output changes with respect to the input. This is the output of the network, ReLU function, and these are your input. Now at this point, if I do some change here, there is no, the output is not changing with respect to input. No matter what it is, the output is always 0, so the output has not changed. Okay, let me plot it here above. Okay, now this is the rate of change. This is the rate of change, and this is your G actually. Okay, so now if at this point there is no change, but from here as soon as G becomes positive, you can see that as the rate of change of that, the rate of change of this output is actually linear with respect to this Z. It means it is always same, it's constant, like 1 there, it's always 1. This is 1. Okay, a small change here, it's like it is basically, suppose you consider a function. What is the rate of change of this function D? What is the rate of change of this function D? What is the rate of change of this variable X with respect to X? That is equal to 1, and that's what is happening. This positive part is just like X equal to X, no? So that's why the rate of change of this function is 1 if the output is greater than 0, otherwise it is 0. Okay, now let's put it like, what is this derivative of Z then? It is like if the output of ReLU, now see, if the output of ReLU is greater than 0, then return 1. The output is greater than 0 means if the output of ReLU is greater than 0, then rate of change of the function is 1. Otherwise otherwise this is equal to this, or it will be 0 otherwise. Otherwise means if ReLU of G is less than or equal to 0. Now see, ReLU is not defined at 0, so you have to put 0 on one side, either that side or this side. So standard implementation, I think, is if it is less than or equal to 0, 0, there is no change, and if it is greater than 0, then it is 1. Okay, so this will be the implementation of act prime if we are using ReLU as an activation function. Okay, I'm just giving you a slow explanation of everything. Don't you think that I'm putting a lots of information there. I mean, it's there, but the thing is that I'm doing it in a relaxed way. I'm assuming that whoever is viewing this video, they have some time and they just want to go through the things there without taking much pressure on that. Okay, so that's what is happening. The backpropagation, what we want to do is now, okay, this derivative, suppose now this thing we can easily write code for, right? I mean, for these we can write code, and for this also we can write code. This ReLU function there, we can write code for it. So now we can easily write, now rate of change of B0 is nothing but O minus Y multiplied by activation prime of Z, where if you're using activation prime of Z in our code, we'll be actually calling this function derivative of Z. That's all we'll be doing there. Okay. Similarly, now if we want to now in the backprop, not only with respect to B0 you have to compute, we also have to do the same thing with respect to W1, and that thing turned out to be same, O minus Y multiplied by this activation prime, more specifically here derivative of G, but I'm writing still activation of prime of Z multiplied by this W1. Like it depends on the corresponding input from the previous layer A1, and this thing is W0 with respect to, if you find this part is same, O minus Y multiplied by activation prime of G, and then this is A0, the corresponding input. That's all. Now in backpropagation we first compute this, and then we update weights. So update weights there, update weights. Okay, now in update weights, what we'll be doing is it's simple now. It's like this B0 equal to B0 minus eta into rate of change of cost with respect to B0, and W0 equal to W0 minus eta into rate of change of cost with respect to W0. Then W1 equal to W1 minus eta into rate of change of cost with respect to W1. That's all. Now, once we have updated that, it's time to now, since we have now new B0, new W0, new W1, now it's time to go back. It's just repeat now. Repeat, R-E-P-E-A-T, repeat. And how many times? When I say this repeat, where it will go? It will go to the forward pass, right? It will repeat again from forward pass. It will again repeat from forward pass there. Okay, with this new W0, W1, and B0, again it will compute the output. It will compute the cost. It will perform this. It will compute the the gradient of the new cost with respect to this B0 and W1 and W0, and then it will update the weights, and again it will repeat. And how many times you want it to do? Like for this simple example, say we control that thing only by one a term that is called as your, say for example, epoch. How many times you want to repeat that loop? That is known as epoch. So we will have some number here, say for example 10 or 20. How many times you want to repeat the thing? Okay, so that's all. Now I have shown you here that okay, we can now actually now write the code for all these things there. Okay, so let's then write the code and see the output. Okay, we are in Google Colab, and now we are ready to write the code. Let's begin. So I'll be importing import numpy, because at some point of time I might use it. So numpy as np, done. And what's next that we want? Okay, let's start with what we have, the hyperparameters. Eta equal to 0.01, say, and the other one is epoch is equal to say 10. We will obviously increase it, but for the time being, let's say 10. And we have this A0 equal to some value, A1 equal to some number, and then we have this desired output as some number. I know the numbers actually. A0 equal to 0.01 0.25, I guess, 0. I know the numbers in a sense like from the example, 15, and then that is 0.0375. Okay, and that's all we have. And then what we want is we want this w0 to have some initial value. You can use now and numpy's random function np dot random dot rand rand, I guess, the function np dot random dot rand within the range of 0 to 1, and w1 is equal to same thing basically, and let's say b0 is equal to 0. Well, let's first see what is this w0 w1 looks like. Okay, so first print w0 so string of w0 comma plus. Let's first see what are these values there. Okay, by the time it connects, let me write a few more lines of code. Suppose w0 we have computed, w1 we have computed, b0 we have computed. Sorry, we have that initial value. Now it is time to do the forward pass. So forward pass. So in that forward pass, what we want to do, we want to compute the intermediate result g such that g is equal to whatever it is this a0, sorry, whatever it is this a0, we want to multiply it with w0 plus a1, multiply this thing with w1 plus add this bias b0. Is it b0? Yeah, it's b0. Where is b0? Yeah, b0. And that's all. That's our z now. Now what we want to do is now we want to pass it through an activation function. So we want our output to be equal to the activation function. So we'll be defining a function now, relu, and there we'll be passing this z. Now we have to, since this is our function, we have to write the code for it. So let's write it. So I'll be writing here. So we'll be defining a function called relu, give it an input say g, and what it does is, as we have seen, activation, the output of relu is whatever it is the input, if it is positive, otherwise 0. Okay, so basically it is doing return by tu and return. We want to return the maximum of 0 and g. Okay, like whatever it is the maximum. So obviously for any negative number, 0 is the maximum, otherwise obviously z is the maximum. So return maximum of 0 or z, we want to return. At the same time, in the same goal, let's write, because anyhow we're going to use it. So we want to define the the derivative function also. See here, what I just did is this part here. The relu of g I have written now. Okay, so obviously we know, like, we have to write the function, this derivative of relu. Actually this function also we have to write, so let's write it. Now what this derivative function is now, if I pass g as input, then inside the derivative function again I have to compute relu of g, right, unnecessarily. But since relu of g is already computed, directly we can pass the value of relu of g here, and we can do some operation. Are you getting what I'm trying to say? Yes. Okay, let's see. What we want is that it is, let's call it a derivative. If I do a spelling mistake, please don't mind. Derivative of the relu, and there what we want is we can pass g there. Like if I pass g, then what we have to do is we have to first compute like relu of g, rj is equal to relu of that z, and then what we want is the derivative is actually if the output is, that is, if the output rg is greater than 0, it is 1, otherwise it is 0, right? That's what we want, isn't it? See, if the output of relu function is greater than 0, then it is 1, otherwise it is 0. Then we can write it in this way, like I know it is return whether return whether rg is greater than 0 or not. If rg is greater than 0, then it is true, it means it will return 1. Otherwise, if it is less than or equal to 0, it will be false, means it will return 0. Okay, so that's what we want. But the thing is that here I'm calling this relu again, because I'm assuming that derivative of relu is taking g as the input, but we can do better than that. Okay, just keep that thing in mind. In a moment I'll be updating that. Okay, now we have O equal to ReLU of G, and output we have computed here. Now it's time to compute the cost. So compute the cost. Now what is the cost then? The cost is equal to whatever it is, O minus y whole squared. So O minus y to the power 2. That's our cost, right? Okay, done. Now it is time to do backprop. So backprop. Now in backprop, the first thing that we have to do is we have to find the rate of change of all these different parameters. So what is the rate of change of the cost function with respect to b0? Let's write it as db. It is the, it is actually db is equal to, let's db equal to, let's say db means, I'm writing a comment for help, db equal to rate of change of c with respect to b0. Okay, that's what I want this db0 to be, and the same thing will be true for all the other parameters. The naming convention will be like that. So okay, what is this db0 is equal to, we have computed it, right? What is the expression? We have we have found the expression, corresponding expression. Rate of change of cost with respect to b0 is O minus y multiplied by derivative of z. Okay, no problem. We can write it now. So it is O minus y is directly coming. It is O minus y, where O is the output generated and y is the desired output. Both these two terms we have, because we have y as constant. O we have computed somewhere here. So at this point, we can write O minus y. The computation will be carried out, multiplied by the derivative of that, activation function. So let's write it like derivative. Since we used ReLU, so let me call this function derivative of ReLU. Now let me write the name right first. This function we have to call actually. So this. Now here, what we can do is we can pass g here directly, like derivative of ReLU. It means what if it is z, then we pass here. That is, according to this definition, we can pass g, because ultimately inside the function we are computing the ReLU of g, and then we are computing the derivative, right? But the thing is that ReLU of g is already computed somewhere, right? This ReLU of g is computed. Instead of passing g directly, we can pass o there, right? That is, we can pass directly o there. And if we pass o, then this step is not needed. Now see, I'm not going to change the name of this variable. I mean, it is not needed that you have to change it to o or something. It's just that, you should know what you're passing, and based on that you have to do the computation. So if we are passing from here o, let this variable be g itself, but what we want is, now we want if g is greater than 0, that is, if whatever this o is coming, if it is greater than 0, it means the rate of change is 1, otherwise rate of change is 0. Got it? Okay, then it is done. We computed it. So similarly, we want to compute now these two terms, dw0 and dw1, O minus y derivative of ReLU o. That's up to that point, everything is same. Only thing is that here we have to multiply this extra thing, a0. See, w0, it is proportional to a0, and then this thing is proportional to a1. That's we have seen there. You see, if you're not convinced, you see, rate of change of w1 is O minus y into activation prime, that is derivative of g function and the activation function, multiplied by a1. If it is w1, it is a1. If it is w0, it is a0. Okay, then you see what we have computed it, and that was the next step. Then update the parameters. Okay, and what we want, b0 will be equal to whatever it is the previous value of b0, subtract it from there, eta multiplied by rate of change of b0, so db0. It's done. Now similarly we can do this, b0 and then w0 and then w1. w0 means w0, subtract it from there, dw0, w0, that's actually, I wrote o. Okay, dw0 and dw1 there. We want to subtract, what did I do? b0 equal to b0 minus eta into db0, w0 equal to w0 minus eta into dw0, w1 is equal to w1, whatever it is the previous weight, minus eta into rate of change of the cost function with respect to w1. This one. Okay, Done. Now we have updated the weight. Now see this again, you have to repeat this forward pass, compute the cost, back propagation. We have to repeat this process as many times as the value of epoch. Okay, okay, then how do we do that? So we just have to put this thing inside a for loop. So for I in range, I in range, 0 to that epoch, 0 to that epoch, and then repeat this thing. So I just have to give the indentation right. So that is it done? Okay, done. Now 0 to epoch, we compute z, we compute the output, we compute the cost. We see this cost, we don't compute like you know, this is for us only so that we can see the cost, and then we update these weights and biases, and then we do these things. Why this thing is coming in is in okay, that's okay, and then we update the we compute the we compute the derivative of those 3 parameters there, and then we update those 3 parameters, and we repeat this process. Okay, done. Now when we repeat, just for our sake, we want to print them. Say for example, I want to print now what is this you know, the output equal to say output equal to string of the output, because that's the output of the network at that iteration, plus we want also to see what is the cost is equal to string of this variable c, string of c. Then okay, let's now run the code. So so we define this function, so I am now executing it. These functions are now defined, and then we want to run this code. So when we run this code, it will actually show us this weight 0 and w1 also. Okay, once at the beginning, only once, and then rest of the outputs will come because of this loop. Initial weight assumed is 0.71 and 0.77, that's all. And then the output is, you can see 0.27, that's the output, and the cost is 0.05, this. Now the output is 0.027. Initially it started with 0.29 and it is reduced to 0.27. It is reducing, and the cost is also when I say output is not reducing, I should not use that term. Output is actually proceeding towards this number 0.0375, whereas the cost function is decreased. Now you see the value of the cost function 0.77 initially it was, and initially it was 0.06, and at the end after the 10th iteration it is 0.05. So you can see that the network has just started learning, but due to this epoch thing so small, it just stopped abruptly there. Okay, but another thing you notice there, these values, the output is moving towards the solution very slowly. Because of that, and that thing is happening because of this small learning rate. Let's improve it, increase it by 10 magnitude. So it means I'm multiplying this step size by 10. Initially it is 0.01, now it is 0.1. Let's see where it goes in 10th iteration. So it goes to 0.07 and it is 0.01. It's like slightly, say 0.15, then it is 0.13, 0.12, point like that. Let's make it say 1, where it goes. Let's see. Okay, have some fun and see where it goes. Is it now 0.0375, cost is 1.8 10 to the power minus 21, very small. The value you see, it is exactly this 0.0375 with this eta. We didn't even have to change this epoch there. In 10 iteration itself was enough. Only thing is that we have to choose this eta equal to 1, but you just do not think it as like a general idea. I mean, if you're training a neural network, for some network this eta equal to 1 could be extremely very large. Okay, and there it might, like, if you know the effect of taking a large step size, right? Yes, certainly up to some extent, increasing the step size takes you to the solution in a faster way. But if you go on increasing it, you will not be able to stop yourself at the bottom. You will just go like that. Okay, so in some sense, so say for example, now if I make it 5, will it reach a solution? Let's see. Now the output is 0, cost is this. At 5 it is somehow it is showing you that the output is 0 and then cost is this. It has not reached that solution. Got the point? So increasing it in arbitrary way is not going to help you always, but up to some extent you can go on increasing. So for 2 also it's not working, so 1 is working. Let's say 1.1, will it work? So 1.1 is not working. Is there anything that I do wrong? So let's see. 1, is it working? Yeah, 1 suddenly it works. Okay, 0.037. Let's say another way I could have figured out could be like I now set it to be 0.1 and then I increase this to 100 or something. So that way also it will do the same thing. You can see 0.3755510. Now this time there is an error there. 0.0375 is not equal to 0.03755. No, like still amount of error is there. What we can do is, suppose if you do not want to change this eta, we want to increase these epochs, the number of iteration, and then towards the end you can see, okay, now it has learned properly. All right, now see, we have used, now see, writing the code was not difficult. Once we can figure out what we have to do, writing code is not a problem. Okay, so now let's now see what will happen. Now we know that this thing is working and we are using relu as an activation function. Now, if we change the input pairs also, then also it should work. Any random number, it should, I should have, I will be able to train the network for. Say, for example, A0 is equal to, suppose, A0 is equal to point, say, 0.89, and this one is also 0.89, and output also we want to be 0.89. Is it a trivial problem? 0.89. I don't know. Maybe A0, if we give 0.89 as the input, output should be also 0.89. Okay, let's see. I run the program and you see output is 0.89. It was very easy, I guess. Okay, let's now change something there. Say if I give the input as 0.89 and the other one as, say, for example, 0.12, output should be 0.009809. Exactly that. Okay, let's run it. 009809 cost is this. So it has learned, like any input output pair, it will be able to learn. But before going further, let me tell you one more thing here. See my initial values, which I have chosen. There was 0.25 when I started my example. It was 0.15, and this was written as 0.375. If you see, the output is actually the product of these two terms there. 0.25 multiplied by 0.15 is 0.0375. Okay, let's see. Okay, let's say 0.25 multiplied by 0.15 equal to 0.0375. That's what. Now, when I say, look, now I train the network, say, now I train the network for these two parameters, and I see that, okay, the network has learned its weights and biases in such a way that if I give the input as, this pair, it tells me the product of those two numbers. Now, it should not give you the impression that that particular neuron has actually learned how to multiply. That is not true. You see why it is not true. Say, so I know, like, if I give this input with the learned weights and biases, it will be able to give me this output. Let's see how do we verify that. Okay, let's write this code here. And what we want is, see, when we train the network, ultimately we know that it has learned this W0, W1, and B0. So take those learned weight 0, weight 1, and B0 and try to compute the output. So what I want is that I want to compute the output. Given a pair of A0 and A0 and A1. Let's start with this itself. A0 is, I'm sorry. Let's start with this itself, A0, A1. Okay, let's start with A0 and A1. Then, do that multiplication and compute that intermediate result based on these learned weights and biases, and then pass that g value through a relu function and then print the output. So in this case, print the output. Now you see, for this pair of input, it is giving you the right output, the product of these two numbers, which is 0.0375. But my point is that you should not get the wrong impression that the network, that particular neuron has learned how to multiply. You see what I mean? Is, say, for example, now I want you multiply 0.25 by 0.1. The output should be 0.025. Let's see what it gives you. It is 0.009. mean, it's nowhere close to the product of those two numbers. Okay, so what this network has learned, or that neuron has learned, is only for that specific training example. And since we have only one neuron, you see, like we don't expect that neuron to learn any general thing. You see, in a deep learning network, there are like millions of neurons there. Each of them are learning some small things, and as a whole, they learn a complex things there. Okay, so only one neuron, you might not be able to, with only one neuron, you might not be able to, construct very, very meaningful, model or network. But why did I take that example? It is, our goal is now only to understand like how backpropagation works and how actually these training things work. What are things that we have to do or we have to take care of when we train a network, or what we actually mean by training a network. So that is what we wanted to understand. And say people have understood the thing. Now the next point is, see, we wrote this code with respect to a specific activation function ReLU. But what if we want to like change this activation function? We just now want to, here I said you, right? Like this activation function could be any activation function. I mean, any means any probable or potential activation function. One we used here is ReLU. The other one is very good candidate is the sigmoid function. Okay, let's say, for example, instead of using ReLU, we want to use sigmoid. Then where exactly in the code we have to change? See, mathematically, we don't have to change anything here because it is activation prime of z. If it is a sigmoid function, then you use the derivative of that sigmoid function. If it is a ReLU function, then this will be replaced by the derivative of that ReLU function. But in the code, you see here where we have to do the change. See, if it is a sigmoid function, then this pair should also be there for sigmoid function also. Right? So let's first write them, like, write this pair for sigmoid function. That it means we should have a function called sigmoid, which we should be able to call whenever we want. This name could be anything, huh? So I'm calling it a sig, and then derivative of sig. Okay, and then sigmoid of g. What is this? Like, what is this sigmoid function? Let me write it. I have never mentioned it here. So what is sigmoid function? So ReLU function we have seen. Now we see what is this sigmoid function. Sigmoid of g is equal to 1 over 1 plus e to the power minus x. Just for a second, let me verify. E to the power, I know one thing, that sigmoid of 0 is equal to 0.5. Now, is it so? E to the power of 0, 1 by 1 plus 1. Yes, right. Now you see, sigmoid of 0 is equal to 0.5 because 1 plus e to the power 0 equal to 1. So 1 by 2 is 0.5. Okay. Now, what is sigmoid of? Now, another thing you see about the sigmoid function is, say, for example, x goes to positive infinity. In that case, what will happen? It means x is an extremely large number. Say, for example, represent that positive infinite by 100. So it will be e to the power minus 100. Okay, I'm just writing positive infinite means x is a large positive number. Say it is 100. 100 is actually large in this case, huh? So it will be like 1 by 1 plus e to the power minus 100 is 1 over e to the power 100, right? Now see, like e to the power 100, it is 2.7, whatever that number, to the power 100 is a large number. So that large number, if you divide 1 by that large number, this entire term will go to 0. So ultimately it will become 1 by 1 plus almost 0, which is equal to almost 1. Okay, now let's do the same thing if it goes to, say, negative 0. Like, say, for example, x goes to minus infinity. Minus infinity, here even you can consider minus 100 as minus infinity. Okay, so e plus e to the power minus of 100, because see, I'm considering like minus infinity, that minus 100, then minus was already there, so it is ultimately 1 by 1 plus e to the power 100. Now we know e to the power 100 large number plus 1 another large number, then 1 over a large number is almost equal to 0. So what we have learned is that if x goes to positive infinity, then the output, that sigmoid of x, it goes to in a positive means it goes to 1, and x goes to negative infinity, it means sigmoid of sigmoid of sigmoid of, what do I do, of that x goes to 0. That's all, right? And sigmoid of 0 is equal to 0.5. Now let's plot it in the form of a graph. It will be more clear in that case. What you see is that this is your, say, x, and this is sigmoid of x, and this is 0, and this is 0.5 in y direction, and in x direction this is 0, say this is 1, and this is minus 1. So when x is equal to 0, we know the sigmoid value is 0.5. When x is equal to 1, it reaches almost 1, so it will be like this. When it is minus 1, it reaches almost 0, so it will be like this. Okay, although I'm not very good, but you can see that it is like this as function, like this way too. Okay, so like that. So this, and in this direction it will remain at 1, in this direction it will, this thing is 1 there, and this thing is certainly 0 there. Okay, so like that. Now if we, when I'll be writing some code in a moment, and I'll show you what is the shape of this sigmoid function. But anyhow, that is your sigmoid function. Now let's see what is the rate of change of the sigmoid function that we need to know, right? So so if we have to write a function for sigmoid, then what we'll be writing is directly this thing is implementable. Okay, like e to the power x and all, we can compute it very easily in Python. So this is directly implementable. But what about these derivative of sigmoid? What is this sigmoid prime? And I'll not go through. It is basically asking ddg of no, I'm writing here g, but I wanted to write here an x there. So sigmoid of x. What is this derivative of the sigmoid function? So it is ddx, rate of change of the sigmoid function, and sigmoid function is what? It is 1 over 1 plus e to the power minus x. That is your sigmoid function. Okay, now that derivative, you can, like, a class 12 student will be a good candidate who will be able to do it very quickly. And you have to follow some standard rules there. And if you follow the standard rules, then what at the end it will turn out to be, this derivative will turn out to be something very interesting. That interesting thing is it will turn out to be sigmoid of x multiplied by 1 minus sigmoid of x. That will be the derivative of sigmoid function. Okay, now here, see, I didn't show you the steps involved, but in a moment using code I'll show you that whatever it is this I'm saying is visually, at least it is right. What I mean by visually right is that, see here, the sigmoid function, you see, sigmoid function looks something like this, no, something like this. Now this is your minus 1, this is, it saturates almost at 1, and this is 0, and this is 0.5, this is 0.5. Now if we plot the rate of change of this function, so suppose now I want to plot the rate of change of this sigmoid function. See here, this is your sigmoid of x versus x. Now I want to plot x versus, rate of change of sigmoid of x. That is basically sigmoid prime of x. Okay, now what is this thing? Now if visually I have to draw it, then how will I draw it? See here, at this point up to this minus 1, there was no change, so nothing will happen, or even if there is a small change, but it is almost 0, right? Now suddenly from here and up to this plus 1, and this is where this, it crosses this line almost like this. You can see that suddenly from here, here I'm talking about, suddenly from here the function starts increasing. Up to this point the function almost increases, so there is this rate of change. You can see, okay, it is going increasing, and then again from here you can see the function slowly goes to this saturation. So slowly goes to this saturation means the rate of change slowly goes down, and again from 1 the function hardly changes. Okay, the change is very small and it's almost 0 like that. So if you plot now what is this rate of change of the sigmoid function with respect to this x, we should get a curve like this. Okay, and that's what we'll try to see by writing some code. Okay, let's first fix that point. I know this video is going longer, but what you can do is that you can I mean, as I said, no, my goal is like, you know, make you people feel comfortable with the concepts and ideas. And I'm assuming that it will have some time. You can see this video in, you know, like you can have multiple cups of coffees or tea in between this process, no problem. And if you want. Now, the point is, now you see here, okay, let me write now the sigmoid function. Okay, now our interest was to write this sigmoid function, sigmoid of z and derivative of z. But before that, let me show you whatever it is that I'm telling you about sigmoid function is true. What I just told you is the definition of, because we want to implement, see, our goal was like, you know, we want to implement the sigmoid and derivative of sigmoid. Okay, for that I have to tell you what is the definition of sigmoid. Definition of sigmoid is this thing is directly implementable, and the derivative of sigmoid turned out to be this is also directly implementable, because if you know what is sigmoid, then it is just like, you know, x into x, 1 minus x, that's all, right? So we can implement it. But you know, I had to show you like that this thing is true, in fact. Okay, and how I wanted to show you this thing true visually, that is, if this is the sigmoid curve, then this should be the rate of, and if it is true, then that should be the curve of the rate of change of sigmoid function. That's my main point. Okay, now let's see whether it's true or not. So it's very straightforward now. You see, suppose we have this z, some anything. Let's say, for example, x is equal to, we'll be taking numpy dot random dot you know, uniform distribution. Don't worry about all this uniform distribution, and we want to take it like from 0. See, we want to basically, why uniform distribution? I can use a range itself, ARANGE. A range within a range of, say, for example, -5 to +5 with a step size, say, 0.1. Okay, that's my x. For all these x's, I want to compute the sigmoid function. Okay, so what I want to do is that, see, x is an array, huh? X is a numpy array now. So we can do something like this. What is the sigmoid of this x? So I want to compute it in this way. Sigmoid of x, sigmoid of, say, x is equal to, what is this? It is 1 over 1 plus e to the power x. So you can write numpy dot exp function to the power of x, or minus x, e to the power minus x, okay, minus x. So this x is an array, so you can perform all these array elements operation in a single go by writing sigmoid of x is equal to that. Let's print it first. Let's see whether it's right or wrong. Print x, and let's print sigmoid of x, sigmoid of x. Okay, and then you try. Sorry. We want to print this sigmoid of x here, huh? Sigmoid of x. Like that. And then it goes, okay, some values are printed, but we want to see in graphical view, so we'll be importing matplotlib. So import matplotlib.pyplot as, say, plot. And then also that's all. Then I want to plot it like plot x versus sigmoid of x. Let's see. I don't want to print them anymore. I just, okay, let's see whether the curve has come or not. So this is a sigmoid function, but I want to get rid of this printing value there. I just want to run it one more time, and you can see that this sigmoid curve has come. This sigmoid curve has come from -5 to +5. You can see this 0.5 is the value at 0, and that's a sigmoid curve. Now, if you, instead of doing -5 to +5, if you want to see from it, you know, this 10, say, for example, -10 to +10, you will see this, you know, this jump there, like -10 to +10. This is the curve. Now we want to now plot the derivative of this sigmoid, right? So how do you do that? Same thing. You can write like sigmoid, no, derivative of sigmoid. So d sigmoid, okay? D sigmoid. The sigmoid is equal to what? We know, like, it is sigmoid of x. Sigmoid of x already computed, so I just want to use this value, this thing, multiplied by 1 minus the same thing, 1 minus sigmoid of x. Now I want to plot it again. I want to plot it with respect to x itself. So I'll be writing this thing, plot it again with respect to x, and then I have to write plot dot show. I didn't write that, but it's a good idea that you write that. And then you can see this curve. You see here, like from suddenly from 0.1 or something here. I mean, there is this rate of changes there, and during 1, I mean, you can see at this point it has saturated. Like at this point here, there's no change there, but at 0.05, I mean at 0, the rate of change is like, it's not changing much or what. It is the highest here. No, rate of change is the at peak when this x is at 0, and it slowly fades away on both the direction, on left and right. So it means visually, at least, I'm showing you that that's the that this is the the derivative of the sigmoid function. But yes, if you are interested in the math, then you can find it out. There are lots of resources over the internet that where you'll find the steps involved in computing the derivative of the sigmoid function. Okay, once we have that, actually, once we know what is sigmoid and what is its derivative, then now we are ready to write this pair of function here. Like what is the code for this function and what is the code for this derivative sigmoid function. And see here, once we have this pair of functions ready, then in the code where we have to do the changes, like wherever we are calling ReLU, we'll be calling sigmoid, and wherever we are calling derivative of ReLU, we'll be calling, instead of this, we'll be calling derivative of sigmoid function. That's all. If we do that change, it will be same as like instead of using ReLU, now we are using sigmoid as the activation function. Okay, before that, let's first write what is this sigmoid function. I mean, what is the code for this sigmoid function? Now see here I already have written it, like sigmoid of x is equal to 1 over 1 plus np exp minus x. I can use it in that way, but the thing is that when I'm using this numpy array, this expression exp function from numpy library, then what it assumes is that this x, it assumes to be a numpy array. But here, if you see where we're calling ReLU of g. Now g is not a numpy array or anything, so it's a number. So I said, like, from here only we want to call this sigmoid function, isn't it? Like instead of calling ReLU, we'll be calling sigmoid. It means we are passing a single number instead of an array to this sigmoid function. So directly we cannot use numpy's exp function. Rather, what we can do, yes, we can do one thing. Actually, we can pack this g inside a numpy array, and then we can call numpy's exp function. That's fine. Now you can do it as an exercise of by yourself. But the thing is, there's a direct way. I mean, there is this library, another library called as math library. Okay, so you can import that math library. Import math. Okay, I don't need a short name for math. Math itself is okay, fine with me. So define sigmoid of g. Here what we want to do is we want to return, see here, what is that? 1 over 1 plus e to the power minus x. Now we have to call this math dot exp function. Okay, so instead of calling numpy's exp function, we'll be now calling here math library's exp function. And this exp function doesn't expect its input to be an array or something. If it is a scalar, a single number, then also it works. Okay, so that's why I'm using math's exp function rather than calling numpy's exp function. Okay, done. And what we want to pass here, e to the power minus x. So e to the power minus of g. That's all. That's our sigmoid function. And what is the derivative of sigmoid function? It's like if we pass sigmoid of x as the as the input parameter to this function, then what we can do is the derivative is nothing but whatever it is z multiplied by 1 minus z. If we assume that g is nothing but it is some sigmoid of x, in that case, derivative of sigmoid function will look like g into 1 into g into 1 minus z into 1 minus z. Okay, that's all. So our two functions are ready. Now what we can do is then in our code, we have to do the changes. I mean, wherever we are calling relu now, we'll be calling. Now see, we are replacing relu by sigmoid. This is where we replace. So instead of calling relu, now we'll be calling sigmoid function. See, here now I'm commenting relu. I'm replacing this relu by its counterpart here, like the corresponding part here, like the sigmoid function. Got it? Done. And where else, this part we have to change. So wherever we are calling this derivative of relu, wherever we're calling this derivative of relu, instead of that we have to call this derivative of sigmoid then, right? It's quite straightforward, right? So derivative of sigmoid, and we are passing C O, we are not passing G, so we don't have to compute again like sigmoid of G there. So since you're passing O, it means this Z is actually O. It means output into 1 minus output, that is sigmoid into 1 minus sigmoid, right? Okay, great. Then what else left? Then nothing else left. I just have to run this. So math I'm importing here, so first I have to execute this block of code again, and then I'm re-executing the program again from the beginning. Now you see our code. Now we are training a network for this pair of input. Input is 0.2515, another one, and then we want our output to be 0.0375. And we already have seen relu work there. Now we want to see whether sigmoid works there or not. Okay, so first let's reduce this number of epochs there, and let's see what happens. Like if we run the code, where it goes 0.52. It started with the initial value or initial output from 0.55. Now it is going to 0.52, but where we want it to go, 0.0375. okay, and cost is like 0.26, and it is 0.23 now. It is cost is reducing, output is going closer to the desired output, and this pair of numbers shows like what is the initial weights we have assumed, like what is W0, what is W1. See, every time I run this code, before actually dealing with this sigmoid thing, before that, let me tell you one thing here about this W0 and W1. Every time we run this code, you will get different pairs of W0 and W1. See, this time this is 0.5 and 0.46. Next time, suppose if I run it, you will get 9.5 and 0.32. Again, if I run it, you will get in a 0.5, 0.36. And based on, since weights are different, initial weights are different, you get slightly different output there of the same pattern. But the thing is, it's not exactly the same. Every time you execute this program, you're not going to get the exact same output because of this randomness of this initial weights. And if you do not want that thing to happen, you just can fix these weights into some fixed number, and every time you execute the code, there will be no everything will be deterministic in that case. Okay, small point I wanted to tell you people. Now that's all. Then now let's see, we want to now see whether sigmoid works or not, and we saw that the pattern is working. So one trick we can do is we can increase the learning rate from 0.1 to 1. Let's see whether it leads us to somewhere or not. It's 0.58. Yes, it is leading us to. Now see, one thing you see, observe here, with eta equal to 1, epoch equal to 10, relu was like, it already got the result, right? But when we used sigmoid, now you see it's not getting the result. It's not like this is the result that we are, we ended up. Now let's see, increase this value eta to, say for example, 2. Does it do any better? Let's see, a learning rate, it is, yeah, okay, but 2 was not tolerable when we used relu. No, you see this thing, see the differences are nice, no? So let's see, 5 means, okay, can I do like any random step, or like 10 if I do 0.09, and this is okay. Is it going? Yeah, it is coming down, no? I mean, it is going closer and closer. With 10 is the eta size. I mean, can I really do it like say 30 this time? Eta equal to 30. I'm just playing with the eta, okay? And you can see it's 0.00022. Cost is this. No, eta, let it be like this 1 only, no problem. And let's increase this epoch to from 100 to 1000. Okay, so let's see what happens. See what happens. It's like 0.04198 and 2.01 10 to the minus 5. I know, some reason I feel like what we want actually 0.0375. It is coming closer, but somehow this thing is 4198. It just moving slowly and slowly. That's the problem with sigmoid, like sigmoid, when it gets saturated, the rate of change becomes very small, so you move basically very slowly towards the solution. So that's really is a point of concern now. Now, can I do something with these random weights is okay. I mean, I'm taking it within the range of 0 to 1. That's fine actually. What else can I do? Then epoch I have to increase like from 1000 to 10,000. Eta equal to 1 I'm considering. And let's see what happens, where it goes. Is it 0.375? Now it's somewhere close, no? 0.037. It has learned it. But you see up to yes, it didn't take me all these 10,000, but let me see what is the minimum that I can do. 10,000 I gave. Let's see whether it does it in 2,000 or not. Okay, I'm being very optimistic this time. With 2000, 0.0375 I want. 2000 it didn't learn. I mean, 2000 epoch was not enough, right? So let's see now, if it give it 3000 now, is it enough? We know 10,000 if we give, it works. And you don't like think that it might be based on these initial random weights, but those random weights I have chosen within the range of 0 to 1. So more or less you can say like that is same, more or less. Okay, so so let's see here where it goes. Even 3000 is not enough. Strange, no? And then I'm giving here, say, now let's jump by one more 5,000, say, a bit more. And 0.0375, it's now close. 0.0375126. So 5,000 it's okay, but with 6,000 I guess it will do the work. With 6,000 epoch and learning rate 1, it will do the job. Okay, 6,000 epoch, learning rate 1, 0.03750. Still it's not very good, huh? You see now the problem with, so give it say 9,000, okay, and then we know 10,000 it was working, so 9,000 should be sufficient. 0.0375, that's the best that it can get, like 0.0375004. See the difference between ReLU and the sigmoid function here. And see here, like say, let me write this code. I mean, copy this code once again, just to see the differences. I mean, I just want to make 2 copies now. This is one, and I want to make a code copy here, and I want to label it like this is for say, this is for ReLU, and the down one is for sigmoid, say. So if it is for ReLU, then I don't need this thing. I want to put this thing in comment and this thing alive, and these I want to like uncomment, and them I want to put inside the comment. Okay, and that's all. Now what we're doing here is in this block of code we are calling ReLU, and then we are using derivative of ReLU. It means our activation function is ReLU. And here in this block of code, we are calling sigmoid, and we are calling, see here, we are calling sigmoid, and we are calling derivative of sigmoid. It means we're using the activation function, sigmoid, as the activation function. Why did I write it twice? Because I just want to see with eta equal to 1, you see here, it was like the benefits of ReLU versus sigmoid. Okay, now see, with eta equal to 1, epoch 10, immediately it learns like, okay, 0.0375 cos 10 to the minus 2, very fast, right? But the same thing is not possible for sigmoid. I mean, you see, even if I like give it like 9,000 epochs, then also you see at the end it somehow is not very good at, or at least as good as whatever ReLU achieved, right? 0.0375000. And also I showed you that 9,000 is like this number, you know, 8,000 is far worse than 9,000 actually. So 8,000 is even not enough to, you know, map the 0.0375 there. So this thing is happening, you see here. Why? Because the learning process is very slow in terms of this sigmoid function there. Okay, I mean, the rate of change, sigmoids becomes very slow once the neuron is saturated, sort of. I mean, see here in this diagram, where was our diagram of sigmoid? Sigmoid, you see there, rate of change becomes smaller and smaller, like only within this range only the rate of change is very high, and that's around there, like when it is the value of this sigmoid function is like beyond like, you know, it becomes closer and closer to 1, the rate of change of that function becomes closer and closer to 0, and that's why it learns very slowly. And you know, that was a problem. And just to, people were actually, initially when neural network was developed, ANN was developed, people thought sigmoid is the perfect sort of replacement, that is what is happening inside our brain, how our brain fires. Okay, what is our activation function in our brain, and the sigmoid maps that activation functions very closely. Okay, it was an inspiration taken from nature. But this problem, people, like when they used it, like they realized like, okay, sigmoid is okay, but the thing is that it becomes very slow, you know, at some points. So people were looking for solutions, and then ReLU turned out to be very nice and very simple solution for that problem. And when ReLU, like when people started using ReLU, they thought like, yeah, in most of the situation ReLU is much better than sigmoid. Okay, but that is again, you know, and that's why you see like ReLU is preferred in almost all the cases over sigmoid function. But anyhow, it's a good idea that we learn about those you know, those famous figures in our history. Like sigmoid is certainly, it will remain as a famous figure in the history of deep learning or machine learning or artificial neural network. It was used heavily, you know, but later on people realized the problem, and they solved the problem by replacing sigmoid by another one called as ReLU. Okay. Okay, then that's all then in this video. I hope you people have you people got the answer which you were looking for when you came to see this video. At least something I am able to like help you in at least in some part. I was helpful. I hope that wholeheartedly. I wish that I was helpful there. But what I try to tell you people is that, okay, let's, with the help of this very simple example, I tried you people to explain you the concepts involved in the training process of a neural network, This is our simple example that I was talking about. So here all the terms are there, like you do the forward pass, you do the backward pass, you do the partial derivative, and you do these, this back propagation where you compute the, derivatives of all these parameters there, so that you can use those derivatives to upgrade or update the, the weights and biases as specified by the gradient descent algorithm. So all these things you have seen in action. And if you have understood this, then more or less the same thing is happening in this deep learning. Like if you consider a big and big and deep network, there also the same things are happening, because in a big and deep network you will find this neuron only. Only thing is that you will find like millions of copies of the same neuron there. They are acting upon obviously different set of weights and biases, but internally they are doing the same operation. They are performing the same operation, and sort of we sort of learned the building block of deep learning or not deep neural network. Okay, then hope people have enjoyed the video, and if you like the video, please press the like button. It will help me, it will help my channel to grow. And also, if you're interested in such videos, then you can subscribe the channel. See you guys with some new content in the next video. Till then, Have a nice day.